So in this video we have 10 different exercises about partial differentiation, and what I want you to do is to write the exercises down on a sheet of paper, tackle them all with pencil and paper, and then having done that you can use the exercises to go through the video, quickly fast forward through, see if you've got them right, and if you've got them right that's great, and if you've got them right you can look at the exercise solution and then perhaps later on try it again and see that you can now calculate the answer correctly. So with that I suggest that you write this down and then pause the video. Okay, welcome back. It's now time to fast forward through the video and to look at the solutions of the exercises which are being presented in this order. So the first exercise was to calculate the partial derivative with respect to x of e to the minus x squared minus y squared. And there are different ways of calculating it. The most brutal is just to say that we're going to use the chain rule, and that this is the derivative of an exponential function, so we're going to get the exponential with the same argument, and then we are going to differentiate the argument, which is minus x squared minus y squared, with respect to our variable, which is here x. This is going to give us minus 2x, and this is going to give us 0 because this is a partial derivative with respect to x, and y is an independent variable, it is different to x. So from this we're going to get minus 2x, so putting the minus 2x in front, we have minus 2x e to the minus x squared minus y squared. So that is our result for this calculation, and I'm just going to also present a different way of approaching this particular calculation, and that's going to be to say that let's look at our initial function and realize that we can write our exponential as e to the minus x squared times e to the minus y squared using the rules for powers. So alternatively, we have d by dx of e to the minus x squared minus y squared means d by dx of e to the minus x squared times e to the minus y squared. This final term here, it does not depend upon x, so I can pull it outside of the brackets, outside of the derivative. So I'm going to have that this is e to the minus y squared times d by dx of e to the minus x squared, and then this is going to give us e to the minus y squared, and then here we have the exponential e to the minus x squared times the derivative with respect to x of the argument, which is minus x squared. Just as above, this is going to give us minus 2x, and this is e to the minus x squared minus y squared using the rules for powers. So this is minus 2x e to the minus x squared minus y squared. So that's just an alternative way of obtaining the result that we first got here. So with that, let's move on to the second exercise. So for this exercise we're differentiating with respect to x to some power y. So for a partial derivative, y, as far as the derivative with respect to x is concerned, is a constant. So all we have to do is just to recall the very standard formula that the derivative with respect to x of x to the n, where n is some constant, is n times x to the n minus 1. And that's all that we do now. So therefore what we have is that d by dx of x to the y is just going to be, we pull the power down and then we multiply it by x to the power minus 1. So that is our result for this exercise. And the key thing to realize is that whenever we're differentiating a partial derivative with respect to x, all other variables should be treated as constants. That is what the definition of the partial derivative tells us to do. So with that, we're going to move on to the next exercise on the next slide. So the next exercise is to calculate the derivative with respect to y of x to the power y. So the variable y is here, and x should be treated as a constant. So this is like working out the derivative of, say, 2 to the power y. And to do that, we use the standard technique of saying this is going to be the derivative with respect to y, and now we want to write the argument here as the exponential of the logarithm of the argument. So this is going to be the derivative of the exponential of the logarithm of the modulus of x to the y. And the reason I'm writing down the modulus is because I'm assuming if y is a variable that x is going to be positive, and this is therefore always going to be positive. I think it's just good practice to write the modulus. So what we have here is, using the rules for logarithms, the derivative with respect to y of the exponential of, and now using the rules for logs, I bring the y down, and that is y times the log of x, brackets, brackets. So now what we have is we are differentiating with respect to y the exponential of y multiplied by what is, for this derivative, a constant. So therefore, using the standard rules, we have that the derivative of an exponential is going to be the exponential of y to the, or y multiplied by the log of x, and then this is going to be multiplied by the derivative with respect to y of the argument to the exponential, which is y times the logarithm of x. Now this derivative here is very easy. It's the derivative of y with respect to y, which is 1, multiplied by a constant, which is the log of x. So I'll bring this constant out front. So all I've done is I've calculated this derivative. It's equal to this, and because this is quite simple, I'm just putting it at the front. And then this needs to be multiplied by this term here, which is the exponential of y times the logarithm of mod x. Now, at this stage, when we look at this, we recognize that this is, just as we saw at the beginning, just a way of writing x to the power of y. So therefore, this is the logarithm of x times x to the power of y. So we conclude that the derivative with respect to y of x to the y is going to be the logarithm of x times x to the y. And with that, we've concluded this exercise. So in this exercise, we want to work out the partial derivative with respect to x of x times sine squared of x cubed y squared. And it's important to notice that there's an x out here, so we need to use the product rule of differentiation. So what we're going to get in this way is that d by dx of x sine squared x cubed y squared, put brackets all around it, is going to be, well, the first term of the product rule is very simple. It's just the derivative of x with respect to x, which is 1, times this term. So that's just going to give us sine squared of x cubed y squared plus x times the derivative with respect to x of sine squared x cubed y squared, close brackets, close brackets. So for this last term, what we have to do is we have to use the chain rule for powers, and what we're going to get is going to be as follows. So I'll just move this somewhat here to the left to give myself a bit more room. So what we're going to get is sine squared x cubed y squared plus, there's an x which was sitting here. When we differentiate sine to the power of 2 of something, we're going to bring the 2 down and decrease the power by 1. So I'll put the 2 in front, and then we have sine of x cubed y squared times the derivative with respect to x of sine of x cubed y squared. So this derivative here is going to give us a cosine multiplied by the derivative of the argument. So we have sine squared of x cubed y squared plus 2x sine x cubed y squared. Derivative of sine, as we've said, is the cosine of x cubed y squared, and then this is multiplied by, and being very slow here, the partial derivative of x cubed y squared. Now this final partial derivative is very simple. It's going to give us 3x squared times y squared. Let's not forget this factor. So what we get is sine squared of x cubed y squared plus 2x sine x cubed y squared cos x cubed y squared times 3x squared y squared. Now let's just try and tidy this up a little bit. Here we have the sine of an argument times the cosine of the same argument, so we could write that, especially with this nice factor of 2 here, as the sine of twice the argument. So 2 sine of something cos of something is the sine of 2 times something, so we're going to get sine of 2x cubed y squared. So putting it all together, we have that the derivative with respect to x of brackets x sine squared x cubed y squared is going to be, the first term was sine squared of x cubed y squared. The next term comes with a plus sign, and we have a 3, we have an x squared and a y squared, but as well as the x squared here, we have an x here, so altogether we have x cubed, and then the 2 and the sine and the cosine through a double angle formula is just going to be the sine of 2x cubed y squared, close brackets. And that is our result for this exercise. So we've used at the end a double angle formula to tidy it up, and I think the other key thing to look out for is at the very beginning to make sure that you recognise through this x here that we have to use a product rule. So let's move on now to the next slide. So in this exercise we want to calculate the partial derivative with respect to y of x times sine squared of x cubed y squared. The only y dependence is here in the argument of the sine, which is itself squared. The x is a constant as far as this partial derivative with respect to y is concerned, so we can just pull it through the derivative. So we have that this is x times the partial derivative with respect to y of sine squared of x cubed y squared. So now we just use the chain rule, and we bring this power down. So 2 comes down here, I'll put it in front of the x, so we have 2x times the sine to the power 1, which we don't need to write explicitly, of x cubed y squared, times the derivative with respect to y of the sine of x cubed y squared. So the derivative of sine is cosine, so we get 2x sine of x cubed y squared times the cosine of x cubed y squared times d by dy of the argument of the sign, which was x cubed y squared, close brackets. And this final term here, we're differentiating with respect to y, so the x cubed is a constant that multiplies everything. We're just going to look at this. It gives us a factor of 2y times this x cubed. So what we're going to have is, well, in exactly the same way as with the previous exercise, the 2 and the sine and the cosine can be rewritten using a double angle formula. So we have from here x times the sine of 2x cubed y squared, and then from our derivative at the end we have x cubed times 2y. So now we can just tidy this a bit, and we say that d by dy of x times the sine squared of x cubed y squared is going to be equal to, we'll put the number 2 in front, there's an x times an x cubed, that gives us x to the 4th, there is a single power of y, and there is the sine of 2x cubed y squared. And that is our answer for this exercise. With that, we can move on to the next slide. So with this exercise, we move on to looking at higher partial derivatives. And this is a second derivative, and what that means is that it is the partial derivative with respect to x of the partial derivative with respect to x of 1 over the square root of x squared plus y squared. So what we have to do is, just as before, calculate this partial derivative, simplify it if needed, and then calculate the next partial derivative, and that will give us our answer. So what we're going to have, just move to the left a little bit, is d by dx of, so the first derivative is of x squared plus y squared to the power of minus 1/2. So we bring the minus a half down, and then we subtract a 1 from the power. So we have minus a half minus 1, and that is minus 3/2. So this is times 1 over x squared plus y squared all to the power of 3/2. And then this is going to be multiplied by d by dx of x squared plus y squared. This final term here is going to give us 2x plus 0, so it's just a 2x. So what we have is d by dx of, there's a minus sign, the 2 and the half cancel, so we're just going to have an x on the top, and on the bottom we have x squared plus y squared all to the power of 3/2. Now we can calculate this derivative, and now we have to use the product rule, because we have x multiplied by x squared plus y squared to the power of minus 3/2. So this is going to give us, there's an overall minus sign, so minus times 1 over x squared plus y squared all to the 3/2. And then for the next term we have minus x multiplying the derivative with respect to x of x squared plus y squared all to the power of minus 3/2 minus, because it's in the denominator. So if we're differentiating this, we bring the power of minus 3/2 down. Minus times minus is plus, so that's going to change this into a plus sign, and we'll put a 3/2 factor here. We then have x squared plus y squared to the minus 3/2 minus 1, and that is minus 5/2. So that's 1 over x squared plus y squared all to the 5/2. And this is then multiplied by d by dx of the argument x squared plus y squared. And just as before, this is going to give us a factor of 2x, and the 2 and the 2 here will cancel. So what we have, therefore, is that the second derivative with respect to x of 1 over the square root of x squared plus y squared is going to be minus 1 over x squared plus y squared to the 3 halves plus 3, and we have an x here, but we also got an x from here. Remember, the 2 and the half cancel, so the x times the x is going to give us x squared, and this is divided by x squared plus y squared, all to the power of 5 halves. And that is our answer for this question. So to do it, we had to use the chain rule for powers, and we had for the second term also to use the product rule. With that, we can move on to the next question. So in this question, we want to calculate the derivative with respect to first y and then x of this function of x and y. And this is called a mixed partial derivative because we are mixing up differentiation with respect to 2, or perhaps more, but in this case 2 different variables. So to calculate this, we need to realize what it means, and d2 by dx dy of x e to the minus x squared y means the derivative with respect to x of the derivative with respect to y of x e to the minus x squared y. So this notation here means first differentiate with respect to the variable more to the right, and then having done that, differentiate with respect to the variable that's initially more to the left. So it's easy now to calculate this. We have to just do this derivative with respect to y, and then having done that, we differentiate what we've got left, having perhaps tidied if needed, with respect to x. So what we have is the derivative with respect to x of, we'll work this out later. Now, here the x factor is a constant as far as the y is concerned, so we can pull it through. So we can just write down x. The derivative with respect to y of the exponential is going to be the exponential e to the minus x squared y times the derivative with respect to y of the argument of the exponential, which is minus x squared y. So this derivative here, the derivative with respect to y of y is 1, so we're going to get minus x squared. So the minus x squared and the x can be multiplied together to give us minus x cubed. So let's do this tidying before we calculate the derivative with respect to x. So we have a minus sign, we have the x multiplied by the x squared, that's going to give us x cubed, and we have e to the minus x squared y, close brackets. And now we do exactly the same thing, except we realize that there is an x dependence here and here, so we're going to have to use the product rule. And what we find in that way, for the first term, the derivative of minus x cubed is minus 3x squared times e to the minus x squared y. And then we have minus x cubed times the derivative with respect to x of e to the minus x squared y. The derivative here of the exponential is going to be the exponential times the derivative of its argument. So just as before, we can calculate this. So we have minus 3x squared e to the minus x squared y. We have minus x cubed sitting here already times e to the minus x squared y times the derivative with respect to x of this argument, and that's going to be, we bring the 2 down, minus 2x to the power 1 times y. So I'll put brackets, minus 2xy. So now we've calculated everything and we can just tidy things up a little bit. And what we find is that the mixed partial derivative d2 by dx dy of brackets x e to the minus x squared y is, now here we have a factor of x squared and an exponential. Here we can take out an x squared and we have the exponential, so they are common factors, so let's pull those out immediately. So we have x squared e to the minus x squared y, open brackets. Now this term here is going to be negative if I've just pulled these out, but here we have two minus signs, so this term is going to be positive if I pull this out. So let me write the positive term first, and we have 2 plus 2 times x cubed times x is x to the fourth y, but we pulled out a factor of x squared, so we have the 2, we have an x squared and a y, and the exponential factor we've already pulled out, and then we have minus 3, and now we close brackets, and that is our answer. And it's always sensible just to check that we've got this right by thinking, if we'd expanded this, would this indeed give us this, and would this give us this? And with that we've calculated the mixed partial derivative of this function here. And what we're going to do in the next exercise, I hope you've already done it, is to calculate the mixed partial derivative of this, but calculating these derivatives in the opposite order. We'll do that on the next slide. So in this exercise we're going to calculate the partial derivative of exactly the same function, and it looks at first sight perhaps like the same partial derivatives, but we've reversed the order. We're taking here the derivative of x first and then the derivative of y. So in other words, what we have to do is we have to calculate d by dy of d by dx of x e to the minus x squared y. And I'll put brackets around that to show that we are differentiating both factors here with respect to x. So it's clear that we now immediately in the first step need to use the product rule. So we have d by dy of, the first term is very simple, it's just x, so we're going to get 1 times e to the minus x squared y. And then for the second term we have plus x e to the minus x squared y, the exponential doesn't change, times the derivative with respect to x of the argument of the exponential, which was minus x squared y. So what we have here is d by dy of e to the minus x squared y. Now this second term here, when we differentiate it, we're going to get minus 2x times y. So minus 2x times y, we can bring the minus 2x outside and multiply it by the x and also the y. So we have minus 2x squared. There's a minus 2x from here times an x, so it's minus 2x squared. There's a y factor, and we have our exponential again, e to the minus x squared y. So now to calculate the derivative of this, I think the easiest thing to do is actually just to say that this is d by dy of 1 minus 2x squared y, close brackets, times e to the minus x squared y, close brackets. So if we do this, we now, from the first term when we're using the product rule, we're going to get minus 2x squared times e to the minus x squared y, and then we're going to get plus 1 minus 2x squared y times the derivative with respect to y of e to the minus x squared y, and this is e to the minus x squared y is e to the y times a constant. The constant is minus x squared, so we're just going to bring the minus x squared down. So I'll put brackets minus x squared e to the minus x squared y. So now we can tidy this up a little bit. We see that we have a common factor of e to the minus x squared y, and that's going to be multiplied by minus 2x squared from the first term, and then we're expanding out this times minus x squared, so 1 times minus x squared is minus x squared, and the final term is minus 2x to the fourth y, because the x squared y is multiplied by x squared, and that's minus and minus, so that should be plus, and then we close the brackets. So now we can just tidy this up a little bit. We have e to the minus x squared y. The first two terms are identical, it's minus 3x squared. The coefficients are different, but the powers of x are the same, I meant, plus 2x to the fourth y, close brackets. We realise here that we can take out a common factor of x squared, so we have x squared e to the minus x squared y, close brackets, and I'm going to write the positive term first, and the positive term is 2x squared y, and then we have minus 3. And this is our result for d by dy of d by dx, so it's d2 dy dx of x e to the minus x squared y, close brackets. So this is our result, and if you compare this with the result of the previous exercise, what you will find is that we have exactly the same result. And this is a consequence of a theorem which tells us that for suitably smooth continuous functions we can reverse the order of mixed partial derivatives and we will get the same result. And that's called Clairaut's theorem. Now, at this stage I want to move on to the next exercise. So, in this penultimate exercise I want to calculate the second derivative with respect to x of the logarithm of the modulus of x squared plus y squared. So again, what this means is that we need to calculate the derivative with respect to x of the derivative with respect to x of the logarithm of the mod of x squared plus y squared. So this is going to give us the derivative with respect to x of. Now, the derivative of a logarithm is 1 over the argument of the logarithm, so that's 1 over x squared plus y squared. So 1 over x squared plus y squared times the derivative with respect to x of the argument, so that was x squared plus y squared. And this derivative is just going to be 2x. So we get d by dx of 2x over x squared plus y squared. So now to differentiate this, we're going to use the product rule. This is 2x multiplied by x squared plus y squared all to the power of minus 1. So it's the product rule together with the chain rule for powers. When we differentiate the 2x, we get 2 over x squared plus y squared. And then we have a 2x multiplied by the derivative of x squared plus y squared to the minus 1. So we bring the power down, that introduces a minus sign. And then we have x squared plus y squared to the power minus 1, which is minus 2. So on the bottom here, we put x squared plus y squared all squared, and then this is multiplied by the derivative of x squared plus y squared with respect to x. So again, this is going to be a 2x factor, and the 2x and this 2x are going to give us 4x squared. So what we have is 2 over x squared plus y squared minus 4x squared over x squared plus y squared all squared. So this is our final result for the second derivative with respect to x of the logarithm of the modulus of x squared plus y squared. And to do it, we've used the chain rule for powers together with the product rule, and we'll now turn to the final exercise of this video. So in this final exercise, what we want to do is to show that this equation is satisfied by the logarithm of x squared plus y squared. In other words, you take this logarithm, differentiate it twice with respect to x, and add to it the second derivative with respect to y of the same logarithm, and it will vanish. And we're told in the question that we can use the previous result, the thing we calculated in the last exercise, which was that the second derivative with respect to x of this logarithm was 2 over x squared plus y squared minus 4x squared over x squared plus y squared all squared. Now, we could just calculate what the second derivative is with respect to y, but what I would like to claim is that it's much easier to use symmetry. So what I mean by this is the following. In our function, our initial function, log of x squared plus y squared, it's invariant under swapping x squared and y squared around. So you can replace x by y by x, and the function will look the same, because the log of x squared plus y squared is the same as the log of y squared plus x squared. So if I know my result for the derivative with respect to x, I can immediately write down the result for the derivative with respect to y. So the second derivative with respect to y of this logarithm is going to be exactly the same result, 2 over x squared plus y squared minus 4, but now the x on the top has to be replaced by y squared divided by x squared plus y squared all squared. So this result is exactly the same as this result. It's just that everywhere here where there was an x, I've written a y, and everywhere where there was a y, I've written an x. And I've not bothered to write x squared plus y squared as y squared plus x squared. I've just swapped it around to keep the same order. So with this result, we can now add the result, and we get that the second derivative with respect to x of the log of x squared plus y squared plus the second derivative with respect to y of the log of x squared plus y squared is going to be, and now I want to put the terms together. This term and this term are identical, so I'm going to get 4 over x squared plus y squared. These terms have got a common minus sign, and they have a common factor of 4, and the denominator is the same, x squared plus y squared all squared. But in the numerator, in one case we have an x squared, that's this term here, and in the other case we have a y squared, so we'll have x squared plus y squared. And what we see now is the beautiful result that here we have an x squared plus y squared, which will partly cancel with the x squared plus y squared squared. So what I can do is I can say that this whole bracket, x squared plus y squared, and this power of 2 will cancel. So we have left minus 4 over x squared plus y squared. But that's exactly this term here. So what we realize is that these two terms, because they have a relative minus sign, are going to cancel and everything will vanish. So this sum of terms actually vanishes. And with that, I'm going to conclude this video, and if you have found any of the problems difficult, what I would encourage you to do is to put the video to one side, having worked through the solutions, and come back and look at it again in a few days and check that you're able to do them without using the solution.